Okay, this is Project Test 8, video number 3, and we're going to go over problems 21 to 30. The height and age of each child in a random sample of children was recorded. The value of the correlation coefficient between height and age for children in the sample was 0.8. So we have R equal to 0.8. Based on the least squares regression line created from the data to predict the height of a child based on age. So basically, we have height over age. And I know this because this is my prediction, which is y over age. Which of the following is a correct statement? On average, the height of a child is 80% of the age of a child. That's not what R is. The correlation coefficient tells us the strength of the regression line. In other words, it tells us how close our data points or our observed points are to the predicted line. In this case, we have a positive relationship, so it's going up, and it's reasonably close to the predicted line or the regression line. The least squares regression line of height versus age will have a slope of 0.8. That is not our slope. Once again, this is the strength of the relationship telling us how close the points are, the data points are to our line. The proportion of the variation in height that is explained by the regression is 0.64. So if I were to square this, I give it R squared is 0.8 squared equals 0.64. So R squared is our coefficient of determination. And our coefficient determination tells you how much variation in Y is explained by X. How much variation in the height is explained by age. This is correct. That is an R squared because they talked about the variation in Y explained by X, and they went ahead and squared the correlation coefficient. All right, these two are just completely wrong. All right, 22. At a certain restaurant, the distribution of wait times between ordering a meal and receiving the meal has a mean of 11.4 and a standard deviation of 2.6. All right, mean is 11.4, standard deviation is 2.6. The restaurant manager wants to find the probability that the mean wait time will be greater than 12 minutes for a random sample of 84 customers. Notice we don't know the shape of the underlying distribution. So we had to have a sample size of 30 or greater. Assuming that the wait times among customers are independent, which of the following describes the sampling distribution of the sample mean? Well, the sample mean is always going to be what we had before. So the 11.4. So that gets rid of this, and that gets rid of this. So we're down to the 11.4. Well, we know it's approximately normal because our sample size is larger than 30. So, but that didn't help us out. And our standard deviation, the standard deviation of the X bar or the sample means does equal 2.6 over the square root of 84. And we know that because the distribution of the sample mean, and remember the sample mean distribution formula is simply this. Okay, so our best answer to 22 is B. Moving on to 23. Two high schools have a similar number of students and parking lots of similar size. The safety officers at both schools want to investigate whether there is an average difference in the number of cars parked per day in the student parking lots for the school year. So we have a random sample of 15 school days will be selected for each selected day. The number of cars parked in the student parking lots will be counted at both schools and the difference will be recorded. Assuming all conditions for inference are met, which of the following is the appropriate test for the investigation? So we know we're not working with a chi-square test, and we also know we're not working with proportion. So we're working with one of these two, and we need to be very careful because this can be tricky. Because we can sit there and say, hey, we have two different sets of data because we have two different schools. But consider this. we have day 1, 2, 3, 4, 5, and 6, all the way out to day 15. And I have school 1's reading and school 2's reading. So I happen to have 2 readings for each day. And so because I have 2 readings for each day, we are actually running a paired test. All right, we're running a paired test because we're running 2 readings for each day. And I have to admit, this is a very tricky problem. It would be very easy to mark B, but since we have 2 readings for each day, we can use a paired test. And why would that matter? Because different days are going to have different amount of kids at school. Basically, we know that Fridays, fewer students are at school on Friday, and typically fewer students are at school on Monday. So consequently, we have a paired because we have 2 readings for every single day, and we can sit there and find the difference from each one. Okay? Tricky problem. Number 24. The histogram shows the distribution of heights of 100 adult men. Based on the histogram, which is the closest to the interquartile range in inches of the distribution? Well, remember, IQR equals Q3 minus Q1, where this is the 25th percentile and this is the 75th percentile. And we have 25% of 100, 0.25 of 100 equals 25, 0.75 of 100 equals 75. So I need to find where 25, the 25th person is, and that'll give me Q1. So I'm going to just start adding up. 1 plus 1 plus 2 plus 2 plus 3 plus 4. Where am I at? Not high enough. Plus 5 plus 6 plus 8. And I went too high, so I'm going to subtract out 8. I go, oh, that's not 8. That's not high enough. So basically, and I'll back up just a second. 1 plus 1 plus 2 plus 2 plus 3 plus 4 plus 5 plus 6. And I got to 24. That's not high enough. But if I add 8 to it, I go over. So somewhere in this bin at 66 is the 25th person. So the 25th person occurs in this bin somewhere. Okay? Continuing on, and now I need to keep going to 75. Plus 10, plus 11, plus 10, plus 9. I'm at 72. If I add 8 more, oh, we now have enough. So it's somewhere in this bin at 71. So 71 minus 66 equals 5. The answer to 24 is 5. Okay. All right, moving on. A state study on labor reported that 1/3 of full-time teachers in the state also work part-time jobs at another job. For those teachers, the average number of hours worked per week at the part-time job was 13. So after an increase in the state teacher salaries, a random sample of 400 teachers who worked part-time at another job was selected. The average number of hours worked per week at the part-time job for the teachers in the sample was 12.5. So we have basically a mean of 13 and an X bar of 12.5 with a standard deviation of the sample of 6.5. Is there convincing statistical evidence that alpha equal 0.05, that the average number of hours worked per week at the part-time job decreased after the salary? So here's what we have. HO, mu equals 13. That's what it used to be. HA, we want to know if it decreased. That's the key word. This is 13, so is mu less than 13? So we're going to go ahead and set up our T statistic because we want the probability of getting a X bar less than 12.5. And T equals X bar minus mu S divided by the square root of N. So we want the probability that T is less than 12.5 minus 13 over 6.5 divided by the square root of 400. Now, this would be the work that you show on an FRQ, but on a multiple choice, you can go straight ahead to the calculator, stat, test, t-test, mean of 13, x bar in this case of 12.5, standard deviation of the sample was 6.5. We had 6.5, and we had a sample of size 400. And we need to make sure we have less than. And when we calculate, we ended up getting a p-value of 0.068. Excuse me, p-value of 0.062. So we need to compare this to an alpha. And they said use a significance level or alpha of 0.05. This is greater. Consequently, we're going to fail to reject the null. So is there evidence? And the answer is, well, we know it's a no because it's greater than, and we failed to reject. Why? The p-value of the test is greater than 0.05, so 25 is A. '26. A city department of transportation studied traffic congestions on a certain highway. To encourage carpooling, the department will recommend a carpool lane if the average number of people in the cars on the highway is less than 2. Based on a probability distribution, what is the mean number of people in passengers' cars on the highway? Well, we're going to do this fairly easily in stat edit. We're going to put this in L1 and this in L2. But here's the way you would do it on an FRQ test. The expected value equals 1 times 0.56 plus 2 times 0.28 plus 3 times 0.08 plus 4 times 0.06 plus 5 times 0.02. That would be work shown on an FRQ test. Here in our calculator, stat edit, 1, 2, 3, 4, 5. And here's the associated probabilities, stat calc, one variable statistics, list in L1 and L2. And I end up getting an X bar equal to 1.7. So 26 happens to be C. Moving on to 27. To compare the effectiveness of 2 treatments, researchers conducted a well-designed experiment using a randomized block design in which the subjects were blocked by age group under 40 and over 40. So basically, we're starting off by a block, and we have over 40, under 40. All right. Which of the following must be true about the randomized block design? Well, once we do this, at this point, we're going to have a random assignment to treatments. Treatment 1, treatment 2. Here, we're going to have a random assignment to the treatment. Treatment 1, treatment 2. Notice I have in each block, the over 40 gets treatment 1 and treatment 2, and the under 40 also gets treatment 1 and treatment 2. The number of subjects in each block is different. That may or may not true. Which of the following must be true? And this is a must be true. This may or may not be the case. Treatments are randomly assigned to subjects within the block. Treatments are randomly assigned. Yeah, we definitely randomly assign treatments within the block. That looks good. The design cannot have a control group. Yeah, this could be a control group. This could be the new medicine. This could be the old medicine. This could be the new medicine. This could be a placebo. So we can definitely have a control group. The experiment uses a matched pair design, not necessarily, not required. The subjects in one block receive one treatment and the other will receive the other treatment. No, both groups have to receive the same treatments. So if I have treatment one here, I have to have treatment one here. Treatment two here, I have to have treatment two here. If I happen to have a T3, then I also happen to have I have to have the same thing here as well. So 27 is B is our best answer. 28. A die in a certain board game has 8 faces. Nice of them. Of which 3 are red and 3 are yellow and 2 are blue. Each face is equally likely to land up when the die is tossed. In a game, a player tosses the die until blue lands face up. All right, so what's the probability of getting a blue? The probability of getting a blue is 2 out of 8 or 0.25. And then we're going to keep tossing until it says we're going to toss until a blue lands face up. So it's possible that this could never happen, but this type of distribution happens to be a geometric. And it's a geometric because you're continuing until the first success. Remember, geometric's the first success, so this is what we're going to do. We're going to keep tossing until the blue shows up. For example, a player who tosses the sequence shown in the table, the following table has tossed the die 3 times before blue showed up. So we tossed it 1 time, 2 times, 3 times. Then we got a blue on the 4th toss. So 3 times before blue or prior to blue might be a better way. Which of the following will toss the die at least 2 times before blue lands face up? So we can toss it once, we can toss it 2 times, we can toss it 3 times, 4 times, ... all the way to infinity. We are interested in at least 2, which means this all the way to positive infinity. Fortunately, I have an at least, which means I have a 1 minus. Okay, so it's a 1 minus, and I'm going to show you 2 different ways to do this. One is, since we know it's a 1 at least, so that makes it 1 minus. So 1 minus the probability that occurs on the first one. Well, the probability of getting a blue here is 0.25. Plus, what's the probability of not getting it on this on the second one? Well, the probability of getting into the second one means I didn't get it on the first one, but then I did get it on the second one. All right, so this is the probability that it occurred on the first one or the second one. And we subtract that from 1 because it's in the least. So 0.25 plus 0.75 times 0.25. And then I'm going to subtract that from 1. And I get 0.5625. If I were showing work, this is what I would show. However, this can also be done on the calculator. 1 minus, we know it's a geometric. We have multiple values here, so this makes this a CDF. All right. And how many trials did we have? 2, with a probability of 0.25. So let's try that out. 1 minus second vars, geometric, CDF, probability, oh, I swapped the order. This should be 0.25. This should be 2. So 0.25 is my probability. This is my number of trials. And once again, I get 0.5625. Either one of those works. In my opinion, this is a more difficult problem. This is not an easy problem. All right. Number 29. A statistical test involves the following null and alternative hypothesis. Which of the following describes a type 2 error? Well, type 2 is a fail to reject the null when the null is false. And by the way, please note, this has the word error. It means it was a mistake. So failing to reject the null when the population mean is 0.64. Wait a second. If it actually is 64 and I failed to reject, that's a correct decision. That wasn't a mistake. That was the correct thing to do. We're looking for errors. Doing the correct thing is never an error. Failing to reject the null when the population mean is greater. So I don't reject this when it is greater. That is a type 2. So this is our answer, but we're going to continue on. Rejecting. Anytime you reject, the only type of error you can make is a type 1, but let's keep reading. Rejecting the null hypothesis. So I reject this and I believe this when the population mean is actually this. That is an error. This would be a type 1 error. All right. Rejecting the null hypothesis when it's greater. So I reject this and I believe this, but it actually is greater. That's actually making a correct decision. That's rejecting correctly. All right. Failing to reject the null hypothesis when the p-value is less than the significance level. That's you made a mistake. That should never happen. If the p-value is less than the significance level, you reject. All right. This is not a type 1 or type 2 error. This is you messed up. Reject when the p-value is less than the significance level. All right. Problem 30. The marketing director for an ice cream company investigated whether there was a difference in preference for 2 new ice cream flavors, cotton candy and mango. Each participant from a large group of people was randomly assigned to taste one of the flavors. After tasting, each person rated the flavor on a numerical scale of 1 to 5. So basically, you can get a 1, 2, 3, 4, 5. Where 1 represents strongly dislike and 5 likes is like. So this is hate and love. All right. A 2 sample T interval for a difference between cotton candy minus mango. So we went CC and mango. This is the order. Was constructed based on the interval. There was a convincing statistical evidence of a difference. If there is a difference, that means it can't contain 0. Well, real quickly, that gets rid of this one because it contains 0. All right. With mango having the greater sample. So we like mango. We love the mango. We hate the cotton candy. We'll get back to that real quickly. First off, my rating scales. I can only have an average between 1 and 5. So any value greater than 1, greater than these values is impossible. So that gets rid of this and this. All right, because we're talking about a mean. So the average value has to be between 1 and 5. Now, if I hate this, that means it's going to have a low score, and this is going to have a high score. So let's just make this the lowest score of a 1, and it's a highest score of a 5. That gives me a -4. That means I'm looking for negative values. The one that has negative values is B. And you're like, well, that's not right. And I said, well, what if this was a 2 and this was a 4? 2 minus 4 is -2. Once again, the mango we loved and we hated the cotton candy. And they told us that we preferred mango. Mango had the greater sample mean. So this had the greater average. So this value had to be larger than this one, but this was our subtraction order, and we ended up in getting negative values. All right, that ends this video.